Okay, let's continue with video 3, number 43. A history teacher believed that students in an afternoon class score higher than the students in a morning class. The results of a special exams are shown below. Can the teacher conclude that the afternoon students have a higher score? Use alpha equal 1%, assume population variances are not equal. We have the data on the morning students and afternoon students. Okay, so let's do this. So we're gonna go to StatCrunch. So for the afternoon students, we have sample size of 41, a mean is 87, and standard deviation of 6.3. For morning students, 36, mean is 84, and standard deviation of 5.8. Let's go to StatCrunch and put the data in there. So you go to Stat, T-stats, to sample with summary, and we're going to record the summaries now. Okay, for the sample one, which is the afternoon students, so we have 41. Sample standard, sample mean is not 41, that's the sample size, it's 87. Sample standard deviation is 6.3. Sample size is 41. For the second one, the mean is 84. The sample standard deviation is 5.8. And the sample size was 36. And now, guys, pay attention to this. If he says population variances are not equal, leave this alone. Don't check it. So turn it off, keep it off, pull variance. If he says population variances are equal, then we check this one. Okay, we need to test that mu1 is greater than mu2, so it's right there, and then hit compute, and here you go. The test statistic is 2.175, the p-value is 0.0164, and since the p-value here is 1%, I believe, let me double check. Yes, alpha is 1% right here. So the p-value is bigger than alpha. 0.0164 is bigger than alpha. We fail to reject the null hypothesis. And then we make a conclusion that there is not enough evidence at the 1% level of significance to conclude that the afternoon students have a higher score than the morning students. Okay? Next question. The table below shows the weights in pounds of 7 subjects before and after following a particular diet program for 3 months. Does the sample evidence suggest that the diet program is effective in reducing the weight? Use alpha equal 1% level of significance. Assume that the difference data come from a population that is normally distributed with no outlier. When you see something like that, the name of the subject before and after data values, then you know that the samples are dependent, are paired. We're going to do this in a different way. We're going to do the difference, and we're going to test whether the difference is positive or negative. Let me show you how to figure out whether you need to test if the mean of the difference is positive or negative. Let's take subject 1. Okay. Was the diet effective in reducing the weight of subject A? He went from 178 to 171. What's 178 minus 171? It's 7. Did it work for this person? It did. And what's the sign of number 7? It's a positive. So then you need to test that the mean of the difference is positive, and that's how we stated that right here. So mean of the difference equal to 0. Mean of the difference is greater than 0, and that should be your claim. So it's going to be t-stats, and we're going to do paired samples. Let me show you how to do that in StatCrunch. I already put the data in StatCrunch. You can see it right here, before and after, right here. So you go to stat, t-stats, but look, guys, not to sample. You have to do paired because it's going to do the difference for you. Okay, column 1 is before, column 2 is after, and then let me show you right here. If I ask you to show me the differences, it's right here, save differences, and we need to test that the mean of the difference is greater than 0 right here. Compute. Okay. T-stats is 1.954. P-value is 0.0493, and what we're testing against, let me just make sure what alpha. So alpha, guys, is 1%. The p-value is bigger than 1%. And then you're going to fail to reject the null hypothesis. And if you fail to reject the null hypothesis, you cannot support the claim. So we're going to say there is not enough evidence at the 1% level of significance to support the claim that the diet program was effective in reducing weight. Okay. 45, in a survey, 46 of 145 women said they regularly remember their dreams, while 140 out of 140 men said they regularly remember their dreams. Does this constitute sufficient evidence to conclude that the proportion of women who are more likely to remember their dreams is higher than those of men? So it's about proportion, P1 and P2 right here. And let me show you how to state the null and the alternative hypothesis. So it will be, HO will be P1 equals P2. P1 stands for the proportion of women, and P2 stands for a proportion of men who remember their dreams. And we need to test that P1 is greater than P2. So it's going to be a proportion stats. Let's take you to StatCrunch. And we're going to go to stat, proportion stats, 2 sample this time, guys, with summary. I have the summary, which is good. All right. Okay, so for the first one, number of successes is 46 out of 145. And for men, it is 40 out of 140. And alpha is 5%. Don't forget to select the right alternative sign. So you need to change this one to greater than. And if you guys want to see the p-value in action, you can select it right here. Compute. Okay, let me show you. Z is 0.6, that's step number 2, 0.57, 58, I'm sorry. P-value is 0.2811, which is a huge, bigger than alpha. We fail to reject HO, that's step number 4. And the conclusion will be there is not enough evidence to support the claim that the proportion of women who are more likely to remember their dreams is higher than those of men. And if you want to see the p-value, guys, it's a huge. Look at the area selected here. When you see too much shading in red, that means you're going to fail to reject the null hypothesis. Next question, 46. Determine if correlation between the two given variables is likely to be positive or negative, or they are not likely to display a linear relationship. The number of crimes committed in an area and the selling price of homes in that area. What do you think, guys, if the number of crimes in an area increase? Very likely people are going to move out and sell their homes cheap just to get out. So actually, there is a negative effect here. So as the number of crimes committed increase, the selling price of homes will decrease in the area because the area wouldn't be attractive to anyone anymore. So the relationship is there, but it is negative. Number 47. A random sample of 9 apples of variety A and an independent random sample of 11 apples of variety B yielded the following weights. Do the data provide sufficient evidence to conclude that the mean weight of apples of variety A differs from the mean weight of apples of variety B? Use alpha equal 10% level of significance. Assume that the sample data come from normally distributed population and that the population variances are not equal. It means pooled is going to be off when you use a StatCrunch. Let's state the null and the alternative hypothesis. So the null will be mu1 equals mu2. The alternative will be mu sub A, if you like, is different from the mean of sub B, or mu1 different from mu2. Mu1 refers to variety A and mu2 refers to variety B, and that's the claim and the alternative hypothesis. So you need to put variety A data in StatCrunch, variety B, and run t-stats. These are independent samples. Okay, let me show you how to do that in StatCrunch. And remember, alpha is 10% right here, and pooled is off again. So already have the data right there for you guys, variety A and variety B. So we're going to go to stat, t-stats, 2 sample with data, not with summary. Selected variety A, select the data in B, variety B, and we're going to run change the alternative hypothesis first, not equal, which is good. That's all I want, and I can run the test now. And one thing I want to bring to your attention again one more time. For pooled guys, it's off because it says population variances are not equal. So you notice I didn't select this one right here. Compute, and alpha is 10%. Step number 2, P is negative 1.064. Step number 3, p-value is 0.3017, which is bigger than alpha. You fail to reject HO, and if you fail to reject HO, you make a conclusion. The following conclusion: there is not enough evidence at the 10% level of significance to support the claim that the mean weight of apples of variety B is different from the mean weight of apples of variety B. That concludes the question. Next question. A teacher figures that final grades in the chemistry. Now this is chi-square distributions questions. A teacher figures that the final grade in the chemistry department are distributed as 20% A, 25% B, 35% C, 10% D, and 10% F. At the end of a randomly selected semester, the following number of grades were recorded. Test the claim that the grade distribution for the department is different than expected. These are the observed values. What he gives us are usually called the observed values, guys. So let's write down the null and the alternative hypothesis and show you, and we'll go from. So the null hypothesis will be distribution of grades is as expected or as claimed. H1 right here will be distribution of grades is different than expected, and that is the claim. And we need to test this claim at 1% level of significance. This is a goodness of fit test. We need two sets of values, the observed values, which are given to us 37, 42, 62, 24, 35. And then we need the expected values, which are the percentages of the total right here. We need to do those manually. So look, the expected values are going to be 20% of 200, which is 40, 25% of 200, which is 50, 35 of 200 is 70, 10% of 200 here should be 20, and 10% of 200 is 20. We need to provide a StatCrunch with the observed values and the expected values in order to be able to perform the goodness of fit test. So let me take you to StatCrunch and show you how to do that. So I'm in StatCrunch, guys. I put the observed values right here in this column, exactly as given to me. The expected value are the percentages of the total, 20% of 200. Oh, the total is 200, guys. If you add them up, you get 200. So 20% of 200 is 40, 25% 200 is 50, 35% 200 is 70, and so on and so forth. And now we're going to run the test. Stat, goodness of fit test right here. Chi-square test. It's a chi-square. Okay, observed values are in O, expected values are in E. And the degrees of freedom here, guys, for your information, is number of categories -1. So it will be 1, 2, 3, 4, 5, -1 will be 4. Compute. Okay. The chi-square is, that's step number 2. You're right, chi-square is 14.469. The p-value is 0.0059, which is less than alpha. We reject HO, and then your conclusion would be the following: there is enough evidence at the 1% level of significance to conclude that the distribution of grades is different than expected. So we support the claim. Remember, p-value low, HO must go, and then if the claim is in H1, we support the claim. Okay, next question. A sports statistician is interested in determining if there is a relationship between the number of home team and visiting team losses in different sports. A random sample of 510 games selected and the results are given below. Test the claim that the number of home team and visiting team losses is independent of the sport. All right. So the null hypothesis, guys, will be the variables are independent, and the alternative hypothesis will be the variables are dependent. So this is what I wrote in HO here. The number of home team, visiting team, and visiting team losses and different sports are independent. The number of home team and visiting team losses and different sports are related or dependent. And here, this time, he wants to check for independency. So the claim is in HO. Usually the claim will be in H1, but this time it is in HO. What we're going to do, guys, we're going to mimic this table in StatCrunch. You have to do that and you use contingency table. So let me show you how to do this. I'm going to go to StatCrunch and look. I enter it exactly as it looks, the table. Look, I put football, basketball, soccer, baseball. I put the numbers. I put right here home team losses and visiting team losses. And then I'm going to show you how to run the test, the independence test. So you go to Stat, Tables, Contingency with Summary. And look, we want the columns that have data. There are 4 columns that have data: the football, basketball, soccer, and baseball. You just select them like that. And then he wants the column that has the labels. The labels is called variable 3. I didn't give it a name, so you just select the remaining one. You just select the remaining one, guys. And if you want the expected count, the expected value, you can select it right here. Let me show you. Okay, expected count right here. And then hit compute. And we're done. So the 39, 155, 25, 80, 31, 90, 15, 75 are the expected values. And the other ones, the one in parentheses are, no, the 39, 155, sorry, 25, 80, 31, 90, 15, 75 are the observed values. And the one in parentheses are called the expected values. So for the chi-square test, we need expected values and we need the observed values, but you don't need to worry about the expected values. StatCrunch can do it by itself. The test statistics, step number 2 is 5.809. The p-value is 0.1213, which is bigger than alpha. So we're going to fail to reject HO. And the conclusion is going to be, this time we're not going to use the word support because the claim is in HO. We're going to say there is not enough evidence at the 5% level of significance to reject the claim that the number of home team and visiting team losses and different sports are independent. Okay, that concludes this question. 50. This is a good ANOVA, analysis of variance, which is pretty much the last section in your book. The times in minutes to assemble a component for 3 different cell phones are listed below. Workers are randomly selected. Test the hypothesis that there is no difference in the mean time for each cell phone. First of all, we're going to state the null and the alternative hypothesis. The null will be that the means are equal, and the alternative will be at least one of the means is different from the other. So the null hypothesis will be mu1 equals mu2 equals mu3. The alternative will be at least one of the means is different from the others. And again, it happens that the claim this time is in the null hypothesis. So we're going to run ANOVA test, and let me show you how to run the test. We're going to go to StatCrunch. We're going to go, I put the data as you can see in variable 3, 4, and 5. You have to put it in StatCrunch first, and you go to Stat, ANOVA, one way. It's a one way only. You select all of them and hit compute. And look, guys, you got everything right here. It's an F distribution, so you're going to look for F. F is 5.298 or 5.30. The p-value is 0.0194, and let me see where we test. So alpha is 5%, and 0.094, guys, is less than 5%, so you reject the null hypothesis, and you say that there is enough evidence to add the 5% level of significance to reject the claim that there is no difference in the mean time for each cell phone. The only time you use the word reject in your conclusion, guys, is if the claim is in the null hypothesis. Okay, now we're going to go to the last question. The data below, last question. The data below are the ages and systolic blood pressures measured in millimeter of mercury of 9 randomly selected adults. Okay, so we're going to put the x values in one variable and the y values in another variable. And it's all about, this is about correlation and regression linear relationships. Find the sample correlation coefficient and interpret its meaning. So let me show you how to do that in StatCrunch. So I already have the data in there. So I'm just going to go to stat, regression, simple linear, X variable, Y variable, and it's going to give me R, and that's what we want. I'm going to show you the value of R right there. Here's R. 0.9598. So it's 0.96. If R is very close to 1, you say that there appears to be a positive linear relationship between the X variable and the Y variable. And what is the X variable here? Age and systolic blood pressure. So the answer here is 0.96. There appears to be a strong positive linear relationship between age and systolic blood pressure. Question B, find the equation of the regression line. You already got it. It's right here, guys. If you let the age be X and the Y be, the systolic blood pressure be Y, you're going to get the equation right here. So it's 63.8 plus 1.4X. 63.8 plus 1.4x. Usually, okay, it's right here. Estimate the systolic blood pressure for someone who is 54. All you have to do, guys, is just plug in x equals what? 54, but make sure that the x, that 54 is within the range here, and it is within the range. The highest is 65, the lowest is 38, so it is between 38 and 64. So if x is 54, and if you plug in x equals 54, what do we get? I got y about 139. Part D, test the claim at the alpha equal 1% level of significance for positive correlation between age and systolic blood pressure. Use the table to make your decision, and this is how you make a decision. If I provide this table and you want to use it, if the absolute value of R, guys, is greater than the critical value, then you reject the null hypothesis and you conclude that there is a positive correlation between age and systolic blood pressure. So what is R here? It's 0.96. The absolute value of R is 0.96 here. And what's the sample size? N is 9, so we have to look for 9. And this is all at the, okay, 9 right here. The critical value, guys, as you can see, is 0.666. And R is bigger than this one. And if it is bigger, then we reject the null hypothesis and conclude that correlation is significant. Here is another way you can do it. Let me show you in the StatCrunch. I'm going to do it one more time. So you go to stat, regression, simple linear. Watch. X variable is X, Y variable is Y. Let me just move this up a little bit. Okay. Testing for positive correlation, guys, is the same thing as testing the slope to be positive, the slope of the line. So just select greater than 0, the slope, not the intercept. Ignore the intercept. Hit compute. And let me show you. Okay. Here's the slope. You see where the line of the slope, you look at the test statistic, which is 9.055, and look at the p-value. It tells me that the p-value is so small, so we reject the null hypothesis. And if you reject the null hypothesis, you conclude that correlation is significant. The null hypothesis here is correlation is not significant, and the alternative will be always correlation is significant. And the last question is going to be about R squared. So let's remember what R squared is here, which is 0.92. So let me take you back. Find R squared and interpret its meaning. So it is what? R squared is 0.92. Change it to percent, it will be 92%. And here's how you interpret the meaning. You say 92% of the variation And systolic blood pressure can be explained by the variation in age using the regression line. End of the review. That's it.